All right, everybody. Today we're going to talk about beta decarboxylation. Let's switch screens and start talking. Beta decarboxylation. We have to know when it happens. And that's pretty straightforward. A carboxylic acid is beta to another carbonyl. It can also happen if it's beta to a cyano group. And there's other instances where it can happen as well, but I'm going to limit our scope to those two. Here's an example. That's an interesting colon. And we'll have this molecule right here. And all we do is heat that molecule up. And we'll see bubbles. What are those bubbles? You'll see CO2 gas created. And you'll also, in this example, make butanone. And if you think about it, what's happened, just from a elemental perspective, is you've excised carbon dioxide from here, right in here. There's the CO2. You're saying, what about that H? Well, let's make that H blue, and I'll show you where that H is. It's right here where there was only one H before, and there's two now. There was a black H. I didn't draw it. There's still the black H, and now there's the blue H. And that is when it happens. And of course, we're more interested in how. We're interested in everything, but let's talk about the how. And to do the how, I'm going to redraw the molecule, do a little rotation. Just a 120 degrees sigma rotation. Don't need to change the color of the pi bond. Carbonyl's down here now, and the H is there. So this has to happen, this sigma rotation, during the mechanism. You don't have to show it on the test. But you'll notice when you do that and get it in this position, there's a nice 6-atom ring that occurs during the transition state in this reaction. The carbonyl is drawn towards the H, the pi electrons. Remember, those are the weakest ones. So it should make sense that they would break first in the mechanism, although you don't need to number these arrows. Your CO2 happens here, and we create a very familiar intermediate during that third arrow. Can you guess what that intermediate is? Well, it's got an O with an H up here and a C double bond to C there. And your CO2 was also made at the same time. and it's an entropy-driven reaction. And this is an enol. It is the tautomer of this ketone. And another driving force for this reaction is that this pi bond, oh, I lost a methyl, didn't I? And before I move on, that's the enol, and I lost this methyl here. Let's put it back on. And this pi bond in this ketone is a much more stable pi because oxygen makes stronger bonds than a pi bond between two carbons. And there are no reagents for this tautomerization to occur. So how does the H move from this position to the alpha position? This is the alpha position that's got to move to right here. Well, the pi bond is going to grab an H from a different molecule, and then the sigma is going to become a pi, and you're going to lose a point if you leave it like that, because this carbon cannot reach this hydrogen. The transition state would be too small, the ring size being 4. So you must add the word intermole on that arrow that says the H comes from a separate molecule that's identical to the one drawn. And there you have it. We have tautomerization. And you get the CO2. So let's do it again. Let's give a mechanism for this. Let's have this one. And this one. I'm going to heat that up. And we're going to create this. This CO2H is beta to this carbonyl. So it's going to decarboxylate. This CO2H is not beta to any carbonyl. There's the alpha position. Is the beta carbon a carbonyl here? No. Is the beta carbon a carbonyl here? No. This CO2H will remain. It's not beta to another carbonyl. Has to be beta, or else you can't do that mechanism. This CO2H is beta to the other, or vice versa. This CO2H is beta to that one. And keep in mind that once one of them's gone, the other will remain and it won't be beta to another carbonyl. So you will have one remaining CO2H. And we will have lost 2 CO2s. So let's do the mechanism underneath. And we need to redraw just a little. Get a bigger eraser going here. And it works just, it's easier to visualize if you put the OH near the other carbonyl, it's beta. And I'm going to redraw both of these down here. So if you draw the carbonyl down here, you better draw the OH Close to, you don't have to. Your mechanism doesn't have to be pretty, but it, it helps to visualize it, I think, if you do it. If you had to pick which one of those is going to happen first, it's a good question. I'm debating on whether I would grade you on that at all. I'm thinking which O would rather be protonated, a carbonyl from a ketone or a carbonyl from a carboxylic acid. And I'm thinking that an acid doesn't want to become a conjugate acid of the acid. That doesn't sound right, does it? Acids don't like being bases. So if I did this on a test and you had 2 CO2s to create, I probably wouldn't care as long as you told me there's 2 things going on. I wouldn't care which one was first for this particular reaction. So let's do the red one first. And this becomes CO2. And get used to this set of 3 arrows that very much reminds me and should remind you. This is an aside up here. We're just sneaking in a little box. There's a molecule that's doing those 3 arrows. I don't know. I didn't think I could turn this off. I think my computer's just having a little conniption here. There's a molecule that looks like this. It's doing this all the time. And becoming its other resonance form. And that magic number of electrons, teachers in science shouldn't use the word magic, I know. But don't the arrows in this box look just like the arrows in the mechanism to the left? And yes, that's the arrows for the resonance of benzene. And 6 pi electrons is a very, very, I don't know how to say it, appealing number of electrons, mechanistically speaking, for many reasons, a few of which are beyond the scope of this course. Wash my hands of that. So you're seeing that kind of arrow arrangement here. We'll see it in about 4 different other reactions before the end of the semester. It's called a pericyclic reaction. You see how these things are going around in a ring-like mechanism? So reactions that involve that, like this one, and the Diels-Alder reaction, and the Cope rearrangement, those are called pericyclic reactions. And we'll do another pericyclic reaction down here. Pi grabs H, sigma becomes pi, and this goes in here. And that's what we get. And let's draw the 2 things. That's one thing. We did it in 2 steps. Remember, you have to make enols. And this CO2H stays. And we have an enol going this way. And it's got 2 OHs on it. And how did we do the... Oh, we don't have it anymore. It was on the previous page. How do we go from enol to the final product? And we had to do what's called tautomerization. We've seen it several times, so seeing it again. And here goes the tautomerization. And it should make sense that if we did the red first, then this probably happens before any of the other blue. Grab H. Sigma becomes pi. Acknowledge the fact that it can't reach by writing intermol on that arrow. Same story down here, light blue. Right, intermole on that arrow. And there's your molecule. We lost the 2 CO2s early. And we generated a ketone here. Oh, we had a ketone. We lost our carboxylic acid here. Why? Because it was beta to the carbonyl here. This carboxylic wasn't beta to any carbonyls, and this one was. And we'll do a cyano before we call this segment quits. Let's do that on a new page. So this carboxylic acid is beta to a cyano. How do I know? Well, alpha is the position 1 away from the carbonyl. This carbon is beta and it's a cyano. So in this one, you're going to get this. And the mechanism, quite simply. And you don't have, I'll show you how you don't have to do the sigma rotation. You just won't see a nice ring of size 6. Here, the pi that grabs the H is the cyano pi. Resonates in. We get something that's going to have to undergo a tautomerization. This is not intermole. Ring size is 6 to get from here to here. And 1, 2, 3, 4, 5, 6. Yeah, there's no problem with ring size 6 in the transition state. We get this. Double bond, C. Double bond, N, H. What else do we get? We got CO2. And we need to make that. So this pi needs to pick up a proton. This needs to become a second pi. Can't reach. Intermole, grab it from another molecule. And that's the end of this segment. And I will come back